The paper titled Design and Evaluation of Skating Motions for a Dexterous Quadruped is the result of work to increase efficiency and speed in locomoting JPL's RoboSimian, whose joints are limited to his peak speed of 3.4 radians per second. To this end, we explored diverse omnidirectional motions for skating with the goal to enable dual locomotion strategies, rolling rapidly on relatively smooth terrain and switching to quadruped walking for rough terrain. We studied trade-offs between using three-wheeled and four-wheeled skating maneuvers over varying terrain. Note the wheels are passive and mounted at the forearms so that no sensing is available at skate contact. Shown first are motion primitives for skating forward in a straight line, first with four wheels and then three wheels. It is already obvious that there is some bias in the three-limb trajectory, causing RoboSimian to turn to the left due to some wheels slipping and less symmetry in the skating motions. Next, we designed diagonal trajectories and compared tracking abilities of three- and four-limb skating over terrains with varying coefficients of friction. For sufficiently high mu, there is not a large difference in error between three- and four-limb skating, although errors are seen on different sides of the desired trajectory. For low mu, we observe some extraneous body yaw at the start of four-limb skating, but the overall trajectory is still followed relatively well. In comparison, three-limb skating has difficulty gaining traction, as seen by severe slip at the start of the trajectory, causing significant body yaw and thus heading error. Next, we designed circular trajectories, shown here with the radius of 2 meters. We observed similar results regarding terrains with lower coefficients of friction, as in the diagonal trajectory cases. For terrains with higher coefficients of friction, both three- and four-limb skating follow the desired trajectories well. Note that error is smaller for higher coefficients of friction in either case, as less slip occurs, especially at the start of the trajectory. For low mu in the three-legged skating case, slip is so bad the wheels are sliding back and forth without rolling at all, completely failing to start up the desired motion until the open loop trajectory is executed almost in its entirety. For rough terrain with varying height, however, four-limb skating suffers from not having consistent contact with the ground for all four skates at all times, removing the exploited symmetry over flat terrain. We observe an inability to traverse rough hilly terrain compared to three-limb skating, which maintains constant contact with the ground. See paper for figures on Monte Carlo trials over terrain with varying heights and coefficients of friction. In conclusion, this paper outlines the design and present performance analyses for a small family of motion primitives for both three- and four-limb skating. Trade-offs are explored between speed and accuracy as a function of stochastic terrain properties. We observe better tracking for four-limb skating over flat terrain, whereas when symmetry can no longer be exploited over rough terrain, three-limb skating is more robust. Although we simulate the trajectories extensively and clamped, we still need to verify them on a real-world system. See interactive presentation or paper for more details.